Hello, now we are going to demonstrate the microstrip passive devices. A popular passive devices is basically a ray trace. This ray trace we are going to be explain. In this experiment, we are going to explain the design parameters and design procedures as well as the simulation of the ray trace coupler. In design steps, we are going to cover radius, how to calculate a radius of ring resonator, and how to calculate the width of ring resonator. Basically, ray trace is your four-port device. Four-port device. In the four-port device, there the this first port is called as a summation port, and the fourth port is called as a difference port. Means suppose the port number 2 and port number 3 is excited by some frequency, you are getting a summation at this port. At the same time, you are getting the difference signal at this port. So if you excite the port number 1, then you are getting output exactly half of the power, equal amplitude at the port number 2 and port number 3, and at the same time you are getting very low power, and this port is very isolated from the port number 1. So you are getting half of the power at port number 2 and port number 3. At the same time, port number 4 are not given any energy at the port 4. And these observation we are going by using a time domain analysis of the ray trace port, where we are going to observe the amplitude and the phase at some port and difference port, the power division between port number 2 and port number 3, and this is the main characteristic we are going to observe in the ray trace, where if we excited port number 1, how much power and how much phase occurs at port number 2 and 3. The first we will see how to calculate the width of ring resonator and the radius of ring resonator. To calculate the width of ring resonator, we have to see this impedance. See these lines having the Z0A and Z0B. These impedance we have to calculate. So we are going to design this steps for ray trace coupler 180-degree hybrid. The consideration thing is characteristic impedance Z0 is a 50 ohm, width along the ring is called W0, W1 is width along the connecting arms, ZOA is the impedance of ring, ZOB is the middle ring section. We required equal power splitting, basically 3 dB. So our K factor means the coefficient factor is equal to 1. So PA is equal to 1 and PB is also 1. PA means power available at port 2 and PB power available at port 3. So the first step to design is the calculating of this ZOA impedance. ZOA is equal to Z0 means 50 ohm into bracket under root 1 plus PA by PB. PA is 1, PB is 1. So this 1 divided by 1 is 1, 1 plus 1 is 2, 2 divided by 1. So under root 2 into 50 is approximately equal to 70.71 ohm. Okay, and again here the PA is equal to 1, PB is equal to 1. So the 1 divided by 1 is 1. So this again answer is under root 2. 2 answer is almost 1.41 into Z0 means 50 ohm. So again here is also you are getting 70.71 ohm. So now for this impedances we have to calculate the width of this ring. Width of the ring is basically we already calculate the impedance. Now our job is to calculate from the width. We have to calculate the impedance. We are designing this ray trace for 2 GHz frequency. So file, go to open device editor. So go to RF tab. We are designing this ray trace by using a microstrip device lines. So calculator, go to permittive is 4.4, loss tangent is 0.09. So this metallization is 0.5, frequency is 2 GHz, and say compute. Okay, and now this compute is over. But here is a 50 ohm for 3 millimeters. So we go for something 1.8. We have to go for the 70.7. Okay, it is near to. So we will go to 1.7, compute 69. So we little bit required 61.61, compute 70.8. Okay, so it's very close to 70.7 ohm. So we required almost 1.61 strip width for the for this area. We have to go for 1.61 width of this track, of the microstrip track. And the second thing is guided wavelength. You can observe here the 84.26 is your guided wavelength. 84.26 and is important because your radius of the ring is calculated using a formula r is equal to 6 into lambda g by 8 pi. So we go to calculators. Our wavelength is basically 84.26. So 84.26 into 6, so that answer is 505, and this is divided by 8 pi, that is almost 42.8, and that answer is 11.81. so your radius of the ray trace is 11.81, means 12 mm you can take it. 12 mm is the basically required for the ray trace coupler. So now our part is over about the design, where we find out the Z0, also Z0B, also the ring radius of the ring, and that is 12 mm almost is we find out, and here the width we find out 1.61 mm, for which will responsible for the 70.7 ohm. Now I requested to Vivek to show the demonstration of the ray trace coupler. So now please Vivek, you just show the demonstration.
Okay, first of all, now we'll open the RF Spice part. This one will go to generic RF components. Then here we are designing right now. It is a rat race hybrid coupler. So I will select as a rat race hybrid coupler. Then we'll specify the details regarding that one. The impedance will be 50 ohm. Then effective permittivity will be 1. Then we are giving a center frequency as 2 gigahertz. Then length in the port segment will be 10. Now what I will do is will complete the circuit by just connecting the parameters components. Now I will connect here R resistance in that one, then resistance in the port 4, resistance for port 1, resistance for port 3. Now we will connect this circuit through wires. This one will be connected like this. Then we'll connect port P4 to resistance R2. Then we'll connect port P1 to R3. We'll connect port P3 to R4. Then we'll connect some this to the for sources. Then this one will be for ground. Sorry, resistance R1 will be also connected to ground. R2 will be also connected to ground. Okay, now we'll select ground to connect everywhere. R1 will be connected to ground. Then this R4 will be connected to ground. This circuits will be P4, P3, P4 will be connected to ground. Then okay, now one more ground is required. This I will connect over here. Now we'll apply some voltage source over it. So just press V to indicate the voltage source. We'll have connect one more ground over it. Then we'll define some input voltage source for that one. You just double click on this one and give input as a sinusoidal waveform or sinusoidal input. The values will be like offset voltage will be 0, peak amplitude will be 1, frequency will be 2 gigahertz, and then time delay will be 0, damping factor will be 0. Okay, sorry, this one will be 0.
Enter
0, enter. Here will then peak amplitude will be 1. Then here I have to go for a frequency 2 gigahertz. Now accept new value. Then all these things remain will be as it is. Okay, now we'll go for a test panel. In that we will do transient test in that basic part setup. We'll select the start time, stop time and everything from 0 to 0 nanoseconds to will go to 5 nanoseconds. Then linear steps will be in pico, 10 pico, and step ceiling will also will be in 10 pico. Now we'll select preset graph plots. For that you need to enter the check the nodes what we have to check exactly. This one will be like this, preset graph plots. Now what values I have to select is like we are giving the input from P1 and we will check the output at P2, P4 and P3. So what we'll check is like V1, V2, V3, V4. Okay, V1, V2, V3, V4. Now this add. Okay, now we'll run this test. What is output is exactly coming. Now we can check it. So first of all I will do is like a single plot, then we'll check through editor what we have exactly received. Go to a tracker part, we have applied input, this one will be our input. Okay, now what okay, just one more thing we have to change in the circuit is like we have to change the values of 51. That's why we are not getting the output properly. 50 ohm for all this. Okay, 50 ohm. Okay, now what we again will check that run the test and we'll check the graphs. Okay, now what we have received the exact graph. See, we'll go to tracker and we'll check the input voltage what we have applied right now. See, this the bigger one is the input voltage. Now what output we are getting at V2 is this one, half of that one, and V3 half of that one, which is overlapping, is on the same phase and it is out of phase from the input. Okay, now what we are getting is V at V4 is nothing, like we are getting a zero waveform. You can check the waveform by clicking this one. So we are not getting any waveforms at V4. This proves exactly the what rat race coupler functionality. Okay, so this is the overall all the four graphs of a rat race hybrid coupler. So we have demonstrated this rat race hybrid coupler.
Now we will change the source from first port to fourth port and check whether the signal is coming to this P1 or not. Okay, so
okay,
here
now we'll change only a port from P1 to P4, that whether the proper output is coming, and that is we are proving that property of a rat race coupler. Okay, now what I will do is just I will connect ground over it and we'll connect through this through wires. Okay, so now the circuit is completed. Okay, this one we have to change a sinusoidal, and in this one we have to make us 2 gigahertz. Okay, now remaining keep it as it is. Now we can run the test again for checking the output. See, we are getting some output. We can verify all these things using a tracker. The V1 now V4 is the input.
V4 is the input.
So it is exactly showing.
Exactly showing. And now we check the V2 and V3. Is the half of the things, and now the V1 is exactly dumping this thing. So exactly reverse operations happens. Means if you excited the port number 4, if you excited the port number this 4, you are not getting any signal at P1. At the vice versa, this case will happen. If you excite at the P1 port, you are not getting at the output at P1. But always you are getting the output at P2 terminal and P3 terminal. And these terminals are equal amplitude, equal phase and half of the power division. So 3 dB power is divided in P2 port and P3 port, and P4 port is isolated. So this basically called as a rat race functionality, where you are getting the summing signal and you are getting a different signals over here. Means if you excite the 1 volt here, you are getting 0.5 volt, 0.5 volt, and here is the inputs are outputs are 0.5, 0.5, and here the difference between this 0.5, 0.0, almost P4 you are getting here. So you can run this port at a different way. Even you can excite the two port P2 and P3, and also you can observe, means if you excite 0.5 volt, 0.5 volt at P2 and P3, you will get 1 volt here and you will get 0 volt here. That also possible. You can also apply the two sources at a time for P2 port and P3 port and see the functionality of the ray trace. Thank you.